My name is Christine Watson. I'm a master's student in materials science and engineering at Oklahoma State University. My advisor is Dr. Pankaj Saran, and I will talk about low-cost ceramic membranes for ultrafiltration of produced water. A brief outline of my talk. I'll give a brief introduction and then talk about the ceramic composite membranes. And then I'll talk about filtration methods that we have investigated and results and conclusions. I'm not going to describe produced water since we talk about that a lot in the seminar, so I'll just jump right into membrane filtration. Typically for produced water treatment, membrane filtration covers microfiltration, which is MF on this diagram, and ultrafiltration, which is UF on this diagram. Reverse osmosis has higher filtration with smaller pore size, but it tends to be more expensive because generally your cost will increase as your pore size decreases. In order to have reverse osmosis filtration of wastewater, you do have to first run your water through microfiltration or ultrafiltration to remove large particles. For our project, we're looking at ultrafiltration, which is between 0.01 microns and 0.1 microns, so right in here. When we're talking about membrane filtration, there's two main types that are used in industry. The first is polymeric membranes, which are lower cost, but polymeric membranes have a limited chemical and thermal durability. Ceramic membranes are more durable in chemical and thermal environments, but they come at a higher cost due to the cost of the raw materials and sintering at higher temperatures. So for my project, I was looking at geopolymer composite, which is low cost while also having the chemical and thermal durability of ceramic membranes. So the geopolymer composite synthesis, first we start with geopolymer, which is an amorphous alkali aluminosilicate inorganic polymer. It's environmentally friendly and non-toxic, and it's low cost because it uses inexpensive materials as the raw materials. So this is a schematic of the geopolymerization reaction. We start with raw materials, which is a aluminosilicate material. We dissolve that in a highly alkaline solution. And from that, we get tetrahedral monomeric silicates and aluminates here. As the tetrahedral silicates and aluminates share oxygen bonds, illustrated here and here, they form oligomers like this. Once the oligomers reach a supersaturated solution, they polycondense and consume water to form the 3D network that we call geopolymer. In the lab, this is how we make geopolymer. We start with potassium hydroxide and silica fume, SiO2, and we add water. We mix those together to achieve water glass. That is our highly alkaline solution. Then we add metakaolin, Al2O3 to SiO2. That's our aluminosilicate starting material. When we mix those together, we achieve a geopolymer slurry, and we cure that at a controlled temperature and humidity to get the geopolymer sample. So these are some pictures showing that process. This is the water glass being poured in. This is the metakaolin that's added to it. We mix it in a thinking mixer, and this is what the geopolymer slurry looks like before curing. The next part of the geopolymer composite is a porous filler because we want to use a porous material to achieve filtration. So for this, we used a zeolite, particularly a clinoptilite zeolite. It has a minimum pore size of 4 to 7 angstroms. And this is a SEM image of the zeolite that we used. This is at 50,000 magnification. And you can see that the pore size is less than 1 micron, which puts us in the ultrafiltration regime. The last part of the geopolymer composite is the support layer for the membrane. For this, we used an aluminum mesh scaffold. And the aluminum mesh is made of aluminum 3003H14, which is 1.2% manganese and has good corrosion resistance. The mesh hole sizes were 0.062 inches in diameter, and the mesh itself is 0.032 inches in thickness. So to sum up all of that, when we put it together, we have a geopolymer slurry, and we have our porous filler, which is the zeolite, and we apply that to the aluminum mesh scaffold and cure it under load. We used 40% volume zeolite in the geopolymer. The zeolite particles themselves were 212 micron to 500 micron in diameter. I found that the optimum curing conditions were 36 hours at 60 degrees C and 40% humidity, followed by a 5-hour ramp down to 20 degrees C. The ramp down is to avoid any thermal expansion mismatch between the aluminum mesh and the geopolymer slurry. After that, I dried it for a minimum of 24 hours before exposing it to water. And the membranes were typically somewhere around 2.23 millimeters in thickness. So to move to filtration methods, I looked at 2 different kinds of filtration. The first one was inflow filtration. In inflow filtration, the feed stream of produced water is perpendicular to the surface of the membrane. You apply a pressure here for the feed stream, and it pushes the produced water against the membrane, and you have permeate, which is the name for the filtered water. The permeate comes out the other side of the membrane. In inflow filtration, you do have particles that accumulate on the surface of your membrane. That is known as caking, and it limits the lifetime of the membrane and the flow rate of your permeate out the other side of the membrane. In crossflow filtration, it's a little bit different. In crossflow, the feed stream of produced water flows parallel to the surface of the membrane. And then you have a retentate feed, which is the name that we use for the flow after it passes the surface of the membrane. The retentate flows out from there. And then you have a permeate stream, which is again the filtered water flows out the surface perpendicular to the membrane. In crossflow filtration, because the feed stream flows to the retentate stream, you have much less caking. You do have some particle buildup on the surface of the membrane, but not nearly as much as in inflow. And in crossflow, the driving force for the filtration process here is that your feed stream and your retentate stream are held at a certain water pressure. And the permeate is usually exposed to atmospheric pressure, and that pressure drop across the membrane pulls the filtered water through. This is a diagram that again shows the difference between inflow and crossflow filtration. And inflow is also known as dead-end filtration or through-flow filtration. Again, you can see here the feed stream presses against the membrane and the particles build up in a cake layer on the surface of the membrane. And in crossflow, because the feed stream is parallel to the surface, the cake layer is much smaller here. These graphs show the flux through the membrane. J is the flux of the permeate through the membrane. RC is the resistance due to caking. And so you can see that in inflow, the flux of the permeate through the membrane decreases as the cake layer increases and the resistance due to caking increases. In crossflow, the flux through the membrane decreases but then reaches a steady state as the cake layer also reaches a steady state, the resistance due to caking. In our lab, we have developed an inflow filtration apparatus. This is where we pour produced water through the top of our apparatus. We have a valve here, another valve with house air coming in, and then it flows down, and then we put the membrane between two pipe joints, and then filtered water flows out the bottom and is collected. For my experiments, I used 30 to 40 psi for the air pressure. I wanted to match the water pressure that I was getting in the crossflow filtration, and that was about 30 to 40 psi. This is a schematic of the crossflow filtration setup. If we start here, we have the feed tank with the produced water that flows to a peristaltic pump, which I looked at 75 RPM and 100 RPM for the pump. And then that flows to the crossflow cell. The crossflow cell has a port with the permeate coming out, which is collected in a tank here. It also has a port for the retentate feed, which goes to a pressure gauge and a valve to control pressure. And then I had the retentate flowing back and recirculating back into the feed. This is an image of the actual crossflow setup in the lab. This is our produced water, which flows here to this Masterflex peristaltic pump. That flows down to this crossflow cell, which is here. It has a port in the top that goes to the permeate tank here, and then another port for the retentate, which goes to the pressure gauge and the pressure valve, and then comes back to the feed tank. This is a diagram showing what's going on in that crossflow cell. You have your feed stream coming in here. It introduces turbulent flow up against the surface of the membrane and flows out into your retentate feed. Then above the membrane, you have a permeate port with the permeate feed coming out the top. So results. The main thing that we have achieved is that we have filtered produced water. You can see here, this is the before and after we get this nice clean looking water. In inflow, the membranes are approximately 1 inch in diameter. This is before what the membrane looks like. And after, you can see the accumulation of particles on the surface of the membrane. Before filtration, the produced water had a turbidity of 63.1 NTU, conductivity at 180.1 millisiemens, and a pH of 6.95. Under 30 and 40 psi of applied pressure, I found that the turbidity reduced to about 15 and 17. The conductivity decreased a little bit, but under 30 psi, but under 40 psi wasn't very significant. The pH increased slightly. That could be due to any unreacted alkaline solution in the geopolymer contribute to that. Crossflow filtration. In the crossflow filtration, the membrane is approximately 1 inch square. Similar to the inflow filtration, you can see the accumulation of solid particles on the surface. So I used the same batch of produced water for inflow and crossflows to get a good comparison. And under 75 RPM and 100 RPM, I got very similar turbidity results as with inflow filtration. The conductivity did decrease a little bit more, and the pH was almost exactly the same as with inflow. The main difference that you get with crossflow and inflow filtration is with the flow rates. So here I have permeate flow rate in milliliters per minute, and along the X I have permeate volume in milliliters. You can see that the flow rate, as the volume of permeate increases, the flow rate of the crossflow is significantly higher than with the inflow. And the crossflow is in yellow and orange at the top, and the inflow is in green and blue here at the bottom. One other thing to note about the difference between the inflow and the crossflow is that inflow is a batch filtration system. That means that you're limited to the size of your apparatus. For our apparatus, we were limited to about 290 milliliters. But in crossflow, you can have a continuous system if you want, or you can increase the amount. It just depends on the size of your feed tank. I ran the crossflow as a closed batch system, but can easily be adapted to a more continuous system. And conclusions, we have successfully designed and processed a self-supporting geopolymer composite membrane for filtration of produced water. We've also demonstrated that cross-flow filtration for produced water has a superior flow rate over inflow filtration, and maintains the similar water quality results that we get with inflow filtration. There's a lot of work that can be done to improve this even further. Thinner membranes would give you a much higher flow rate through the membrane. Also, to look at temperature studies, all the experiments that I conducted were done at room temperature, and it would be interesting to see at a higher temperature how the filtration would vary. The crossflow filtration can also be adapted to a tubular membrane geometry, which makes it more practical for industrial applications. And then reusable membranes are a big topic to look at through backwashing or cleaning, and being able to reuse that membrane, which would lower the cost and lower the environmental impact. And finally, varying the aluminum alloy, trying different aluminum types to see if it affects the bonding with the geopolymer or the filtration performance. And I'd like to thank the OSU Office of Vice President of Research for funding this project. And that is all that I have. So any questions?
Very good presentation. We do have some questions. If you want to unmute yourself, you can go ahead and ask those.
Yeah, I have a question. It's a nice work and presentation. And coming to that experimental measurements, so are there repeatability tests like slide 24 or maybe 21?
For this one, are you saying if I did more than one experiment?
Yes, at each condition.
Yes, I did. This is an average of the multiple tests that I conducted. The 75 RPM, you'll notice, is much smaller. I used a smaller volume with it. That's because this is an ongoing experiment and an ongoing study. So I am doing more experiments to see if the crossflow membrane can handle a higher volume, and how high a volume that could be.
Yeah, including the standard deviations in the plot would be, good actually. So just to know, like, how, much repeatable the experiments are, especially if you go to slide 21, I'll take a few more seconds. Yeah, so you got that weird trend, right? I mean, like at 30 PSI, you got like low turbidity compared to 40 PSI. But the conductivity is, you got a drop and then increased again, right? Just to make sure that the trend that you observed is indeed the correct trend. I mean, maybe doing multiple experiments to see like if observation is still valid, that would be good.
Yes, this is an average of the values that I achieved, but you're right, including the standard deviation would give you a better presentation of the results.
Sure. Thank you. Yeah.
Thank you. Dr. Momodi was next.
Yeah, well, I'm not doctor yet, I'm a PhD student. Thank you, Kristen. It was a good talk. I have a couple of questions. First of all, did you have any chance to measure the pore size of the membrane?
Say that again.
Did you measure pore size of the membrane?
The pore size of the membrane. We are measuring that now.
Okay, so you have not measured it yet, am I right? So and in slide 21, well, once we treat produced water, we need to understand the mechanism, how we can remove salt, how we can remove oil component. In this case, did you measure total dissolved solid? I mean, or total organic carbons for after treating produced water, or you just measure the conductivity?
We measured conductivity. So TDS, total dissolved solids, is equal to the conductivity factor times the conductivity. And I wanted to, instead of using a, typically for produced water, the conductivity factor is very high, but I wanted to measure that directly so that I can get an accurate TDS measurement. And that's also something we're working on right now.
Okay, and based on your result, at 30 PSI gauge, you got almost 20% reduction. And okay, and would you please go to slide 24 or 23? Yeah. How long did it take for crossflow? I mean, the time that you run the experiment for crossflow and didn't system.
Typically for the inflow, it can between 1 and 2 hours is when it reaches 290 milliliters of permeate volume. The time there, it slows down significantly as time goes on. For the crossflow, I can reach 300 milliliters easily within an hour.
Within an hour?
Yes, it's much faster.
It's much faster. It's because of the fouling, I assume. For dead-end system, 2 hours. Okay, thank you.
Okay,
Quick question on your flux. Here you said permeate flow rate because you did 2 experiments. Were the membrane area the same for both the dead end and the cross flow? Because you didn't write or you didn't actually estimate flux rate, which is mil per centimeter squared or per meter squared per minute. So were the same area used for the 2 systems?
No, the membranes are similar in size, but not similar in geometry. So the inflow is 1 inch in diameter.
That's all right. I mean, that's
round.
something that think about when
Yeah.
you do the
And-
evaluation on the
Yeah.
permeate rate.
Yeah.
The second thing, when you have your setup, your feed tank, let's call it, or this beaker is very small, and that typically would change the property of the constituents there. I would suggest if you use larger volume feed tank, that would reduce the variability in the feed tank and have the continuous consistent property of the feed to the membrane. In addition, maybe you consider also using flocculant to get rid of some maybe oily material. I didn't know what type of feed you did use, but that's something that you could consider as well, because you get like some grains in brownish color. I don't know what they are, but that's something you may also consider. It's a good presentation. Thank you.
Thank you.
Are there any other questions? I only had one. I guess I'm curious, are you going to, or have you already done a detailed analysis to see what you're removing? Again, it's, you're seeing a significant reduction in the turbidity, so you're obviously cleaning up the water, but the TDS reductions were relatively small. So I'm curious, what you are removing and if you've analyzed that.
We're working on that now. Some of the past results from our group have shown that we do still have a lot of dissolved salt in the filtered water.
Mm-hmm. Okay, well, thank you very much. Enjoyed your presentation, and good luck as you continue your research.
Thank you.